Angles in radian measure. Alright, let's first see what a radian actually is. So looking at this illustration, imagine we have a circle, we have the center of the circle, and we're looking at the radius. Now we know that the radius is from the center of the circle to the circle itself. Now we'll denote the radius as r, and imagine that we start right here and we start following this outer arc of the circle, okay? Meaning on the black edge of the circle. And imagine that even though this is a curved line, that we try to make that curved line exactly equal to the radius itself. So for instance, if the radius is 10, then this arc of the curve would also be equal to 10. Now, when we have opened up to an angle where the radius is precisely equal to the length of that arc, then we say that that angle theta has a measure of 1 radian. Okay? You might notice by looking at the illustration that that looks like it would be at least close to a 60-degree angle. And it's not exactly equal to a 60-degree angle, but that's not really all that far off, as we'll see in just a little bit. Now, using the idea from the previous slide, if theta is being measured in radians as opposed to degrees, then we say that theta equals the arc length, which we'll call s, over the radius, which is equal to r. So when the arc length and the radius are equal to each other, then theta will equal 1. Well, let's consider an example where s is not equal to r. So suppose that the arc length is equal to 15 units, and the radius, on the other hand, is equal to 5 units. Well, then using the formula above, we would have theta equals 15 divided by 5, which equals 3. So that is 3 radians. What you'll find is that in trigonometry, we generally don't bother to write the word radian. We'll only, in this course, we'll be using 2 measures, degrees and radians. So if you don't see a degree symbol, then you are to assume that it is a radian. Now, an interesting question would be, how many radians are in a circle? Well, we use the formula theta equals arc length over radius, that is s over r, and let's look at the circle over there on the right. Now, if I were to go all the way around a circle, like let's say this is my starting point here, so I start going around, I keep going around all the way here. Excuse the rough drawing there. Well-known fact from geometry, which I suspect you'll recall, is that the circumference of any circle equals 2 pi r. Well, notice if we went all the way around the circle, then the circumference would be the same as the arc length. So for a complete circle, what we would have is theta equals the arc length, 2 pi r for a complete revolution, over r. Those r's would cancel out, and we would have 2 pi. So there are 2 pi radians in a circle. This is analogous to when you have degrees. There are 360 degrees in a circle. So we could say as an equivalence that 360 degrees equals 2 pi in terms of radians. Now, of course, we could simplify that relationship by dividing both sides by 2, and if you do that, what you'll have is that pi radians equals 180 degrees. Now, if we form a fraction of those, the left and the right hand side, what we would either have would be pi over 180, or we would have 180 over pi. These two fractions are the conversion factors that we can use if we're converting from degrees to radians or radians to degrees. And you don't really have to specifically memorize which conversion factor is for which conversion, as I'll just show you in a moment. Just keep in mind it's going to be one of those two for each problem, and I'll show you how to select the right one. So here in this example, we're going from degrees to radians. So we have 210 degrees. So we're going to multiply by one of the conversion fractions on the previous side. Well, 210 is in terms of degrees, so we want degrees to cancel out. So that means we would want the 180 degrees to be in the denominator so that degrees will cancel out. So the correct conversion factor would be pi over 180 degrees. So you see, if you cancel out degrees, what you'll have is 210 pi over 180. Well, of course, that could be reduced. Suppose we divide numerator and denominator by 10. We would have 21 pi over 18. We could further go and divide 21 and 18 by 3, and we would have 7 pi over 6. So 210 degrees is equal to 7 pi over 6. Let's look at the other direction now, where we'll take radians and we'll convert it to degrees. So we have 3 pi over 4. Well, we want our answer to be in terms of degrees, so what we'd better do is put the 180 in the numerator so that our answer will continue to have the degree symbol. So it would be 180 over pi. Now the pi's will cancel, and after canceling out pi, you would have 3 times 180 degrees over 4. 4 will go into 180 45 times. So finally, 3 times 45 would be 135, and of course we still have our degree symbol. We've successfully converted from radians to degrees. So as long as you use the correct version of that conversion factor, 180 degrees over pi or pi over 180 degrees, you'll be fine. Now there's some common angles that will come up over and over in the study of trigonometry. I've listed the angles corresponding to the quadrants, called quadrantal angles: 0, pi halves pi, and 3 pi over 2. 3 pi over 2, keep in mind, would be 1.5 pi. So it's 2 pi all the way around. Next, we could look down the center of those quadrants. We'd have pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Next, we'd have pi over 6, 5 pi over 6. Notice that the angle here up to pi over 6 is the same as this angle here. And then we'd have 7 pi over 6 and 11 pi over 6. And finally, the blue lines, pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. These are the exact same angles that you saw me do in the previous lecture where we were doing degree measure, if you watched that. If not, it would be a good idea actually if you went back and watched that. When using radian measure, we're normally going to express our angles in the form theta is between 0 and 2 pi. 0 and 2 pi would describe the same angle, so we'll use 0 in that case. Notice there's no equality on 2 pi. Recall that if we were having this discussion for degrees, we would keep things, we would keep things between 0 and 360 degrees. We're going to finish up this lesson by looking at some coterminal angles. Let's say we have 17 pi over 6. Now, please keep in mind that over here, this would be pi radians. That would be the same as 6 pi. 6 over 6 is 1. Why did I choose 6? Because in this angle we're going to look at, the denominator is 6. Now, 1/6 would look like this. You'd start here. You'd go 1, 2, approximately 3, 4, 5, and 6. So let's take that 17 over 6. When we've gone this far, we've gone 6/6. If we go around another half circle, at this point we would be 12/6 pi. Now from 12/6 pi to get up to 17/6 pi, we'd have to go another 5/6. 12 plus 5 would give 17. So 1, 2, 3, 4, 5. Approximately that angle there. And notice, since the first revolution of 12 pi over 6 we were, you might say, spinning our wheels, it'd be more precise to just describe that original angle as that 5 pi over 6 that was left over after we made a complete revolution. So 17 pi over 6 and 5 pi over 6 are considered coterminal. They get you the same place. The one on the right is preferred. Let's do one more example, this time with a negative angle. Now again, over here, this is pi. We're looking at force in this case, so that's 4/4 pi. And we're going in the negative direction. So let's break up a half a circle into fourths. That would be, here I'll mark them in red, starting here, 1/4, 2/4, 3/4, 4/4, 5/4. Just mark them all. So in the negative direction, that would be negative 4 over 4. To get to negative 5 over 4, we have to go one more mark there. That would be it. And notice that we don't need to use a negative angle. It could have been more concisely described as 1, 2, 3 pi over 4. That's a positive angle, and it's within the first revolution. This is the way we'll normally write these. All right, we're done. Good luck.